Hi everyone, my name is Junyoung Kim. I will introduce about my research hybrid position torque anchor controller for minimizing ZMP error of humanoid robot. When generating the walking pattern of the humanoid robot, the linear inverted pendulum called the LIPM is widely used. The LIPM has the advantage of being able to generate analytic walking pattern, but there is a model error with the actual robot. Due to the model error, the error between the desired GMP and the actual GMP occurs. To overcome the GMP error caused by the model error, studies using ankle torque have been conducted. However, if torque control is performed without controlling the position of the ankle joint, two problems can occur. First, when a large disturbance is applied to the robot, the excessive torque can be applied to the ankle joint, and the foot can tip over. Second, it is difficult tracking the task level trajectory like COM. To solve the previous two problems, the proposed hybrid ankle controller can overcome these limitations. The hybrid controller has the advantage of being able to control position and torque at the same time. The proposed hybrid ankle controller consists of position controller and torque controller. So when we use the hybrid ankle controller, we can control the position of the GMP and track the steering trajectory at the same time. Especially, the estimated torque using MOB is used for torque feedback control loop of the proposed controller. The algorithm can be implemented without joint torque sensors and not be affected by sensor noise and bandwidth. As a related study, the first video is the previous research about ankle torque control for ZMP tracking. Although the performance for ankle torque control has been demonstrated in previous research, the limitations mentioned in previous slide exist. Also, there are some studies to improve GMP tracking performance by modifying the COM trajectory aside from using ankle torque control. However, the method to modify task trajectories such as COM or capture point for the ZMP tracking has slow responsiveness to sudden disturbance. Unlike this study, another example of using a hybrid controller for a humanoid is the study on the right. In the study, the hybrid controller was used to control the contact force at the task space level. From now on, we will explain the proposed hybrid ankle controller. To track the desired joint position trajectory and desired joint torque that can minimize the GMP error, we designed the hybrid position torque ankle controller. The joint position controlled humanoid robot has the desired joint position trajectory calculated from the IK to work with predefined walking patterns. A PD controller is used for joint position control to track the desired joint trajectory. Torque controller is used to minimize the GMP error and consists of a feed-forward controller and feedback controller. Finally, the commanding torque of the ankle joints can be calculated as the sum of the position control torque and the torque control torque. To obtain the current joint torque to be used for torque feedback control, it was estimated using MOB. By using this joint torque estimate using the model-based observer without using a sensor, our proposed algorithm can be used without a joint torque sensor and ensure control performance regardless of sensor noise and bandwidth. Also, the closed-loop internal stability of the torque controller is enhanced by using the model-based observer. We can formulate momentum and observer dynamics of robot. By subtracting the observer dynamics from the momentum dynamics, we can obtain a low-pass filter form of the disturbance torque. Finally, the joint torque can be estimated by adding the commanding joint torque and the estimated joint disturbance torque. The method to calculate the desired anchor joint torque for GMP tracking is as follows. The anchor torque is calculated so that the moment applied to the desired GMP position becomes zero through the contact force measured on both feet. From the first equation, the torque required for the ankle to make the desired GMP can be obtained from the desired GMP position and the force of the both ankles measured from the force sensor. Anchor torque distribution ratio required to distribute the anchor torque is obtained as in the third equation. In the double support phase, the anchor torque distribution ratio is determined depending on the distance between the position of the GMP and the both feet. Also, in the single support phase, the anchor torque distribution ratio is determined so that the desired anchor torque can be applied from the supporting foot. Finally, considering ankle orientation, both anchor torques are determined using a distribution ratio respectively. The performance of the proposed controller was verified using Tokabi in the Bunzoku simulator. Tokabi has 6 DOFs for each leg, 8 DOFs for each arm, 3 DOFs for the waist, and 2 DOFs for the head. Tokabi has a height of 180 cm and a weight of 100 kg. In the simulation, the humanoid Tokabi walks a total of 1 meter with a stride of 10 cm, and the walking time of one step is 1 second. The real ZMP was measured using the force torque sensor attached to the foot. When the proposed hybrid ankle controller is not used, the measured ZMP on the x-axis increases sharply owing to the motion of the swing foot during the swing phase. In addition, during the landing phase, the measured GMP on the x-axis decreases sharply owing to the impact force generated when the swing foot lands. In contrast, when the proposed hybrid ankle controller was used, the error of the GMP in the x-axis direction was reduced by about approximately 54.8%. Furthermore, after using the proposed hybrid ankle controller, the error of the ZMP in the y-axis was reduced by approximately 23.4%. When the proposed hybrid ankle controller is not used, the measured GMP in the y-axis moves out of the support polygon area. However, when the proposed hybrid ankle controller is used, the measured GMP in the y-axis converges to the desired GMP reference and exists in the support polygon area. To verify whether the proposed hybrid ankle controller can maintain stability by reacting immediately with the external force, in the simulation result, the humanoid Tokabi walks a total of 0.5 meter with a stride of 10 cm and the walking time of one step is 1 second. The 200 Newton of x-axis external force was applied to the torso of Tokabi for 0.3 seconds in 6.1 seconds when the swing foot lands. When the proposed hybrid ankle controller was not used, the humanoid failed to maintain stability against an external force. However, when using the proposed hybrid ankle controller, the Tokabi was able to maintain stability by applying the ankle torque to minimize the GMP error due to the external force. The proposed controller is not used, the GMP comes out of the supporting foot by external force. In contrast, when the proposed controller was used, it was confirmed that GMP was controlled and did not go out of the supporting foot even against the external force. The high torque feedback gain allows humanoids to maintain stability even under an external force of 200 Newton. When a stronger external force is applied, the higher gain of the torque controller is required for the humanoid to maintain balance. The simulation results show that the humanoid robot with the proposed method can maintain its stability when an external force up to 200 Newton is applied to the robot. Finally, in this study, the hybrid position torque and controller was proposed to minimize the error of the GMP. The hybrid controller is used to track the desired joint position calculated from the IK and apply the desired joint torque to minimize the GMP error simultaneously. For torque feedback control, the torque of the anchor joint was estimated using MOB. As a result, the proposed hybrid anchor controller can be used without joint torque sensor. Throughout the simulation, it was confirmed that the ZMP tracking performance was improved when the proposed controller was used. In addition, with the proposed hybrid ankle controller, we confirmed that the humanoid can maintain its balance against the external force as well. Our future work will involve conducting experiments by applying the proposed controller to a real robot and proving the robustness of the hybrid position torque and controller. Thank you for listening my presentation.